Shall we start, sir?
Yes, please.
Ellarigu namaskara. A very good morning to everyone. The very concept of science is all about what, why, when, and how. These curious questions have led to extraordinary innovations, inventions, and discoveries. And we are here to celebrate and commemorate one such invention, the Raman effect, by India's one of the greatest scientists, Sir C.V. Raman. Highly distinguished chief guest, Padma Bhushan, Professor P. Balaram, respected director, Dr. Sridevi Annapurna Singh, dear colleagues, students, ladies and gentlemen, and everyone who have joined for this meeting. On behalf of CSIR-CFTRI Mysuru, I would like to extend a cordial welcome to all of you to this important and an historic occasion of National Science Day. National Science Day is celebrated each year on this day, that is 28th of February, to mark the discovery of Raman effect by Sir Sri C.V. Raman. I quote, "Success can only come to you by a courageous devotion to the task lying in front of you, and there is nothing worth in this world that can come without the sweat of your brow," said Sir C.V. Raman. These words speaks volumes of his personality and dedication, which bestowed him with the Nobel Prize for Physics in 1930. With this note, may I now request our director, Dr. Sridevi Annapurna Singh, to welcome and introduce our chief guest to the gathering. Please, ma'am.
Thank you, Dr. Purnima. A very good morning to all, and I wish everybody present in this event a wonderful National Science Day. Padma Bhushan Professor Balaram, CSIR-CFTRI family of retirees, faculty and students, ladies and gentlemen. As we all know, this day commemorates the discovery of the Raman effect, for which the Nobel Prize was awarded in 1930. The Raman effect is a very weak effect. Only 1 in a million of the scattered light particles or photons actually exhibit the change in wavelength. In the first 7 years of its discovery, the Raman effect was the subject of more than 700 papers in scientific literature, mostly by physicists who were using this technique to study the vibration and rotation of molecules and relating these phenomena to the molecular structure. This unique spectrum of Raman scattered light for any particular substance served as a fingerprint that could be used for qualitative analysis, even in a mixture of materials, including food. By the late 1930s, the Raman effect had become the principal method of non-destructive chemical analysis for both organic and inorganic compounds. And unlike many other analytical methods, it could be easily applied to the analysis of aqueous solutions. And the intensity could be related to the amount of the substance, thereby making it quantitative. Raman spectroscopy could also be applied not only to liquids but also gases and solids. This National Science Day is celebrated every year to motivate students to study science. It is celebrated in India in schools, colleges, universities, and scientific institutions, amongst others. The Union Minister for Science and Technology, Dr. Jitendra Singh, in the company of government representatives for science and technology, launched the theme of this year's Science Day on 5th January 2022. This theme is Integrated Approach in Science and Technology for a Sustainable Future. He highlighted that a fourfold integrated approach in science and technology for sustainable future would help us to come out of a culture of working in silos, as suggested by our Prime Minister, to play a leading role in the global arena. The fourfold approach would consist of integration of all the scientific departments which can work on theme-based approach, extended scientific integration encompassing engineering, medical, and other institutions. Extra scientific integration involving identification of the needs of other ministries. It could be Jal Shakti, railways, and so on. And extending science-driven, all-inclusive approach integrating startups and industry. This year's theme is well in line with the mandate of our institute that is working for over 7 decades on integrated processing of the nation's agri-produce through science and technology interventions. Integrated processing will lead not only to value addition but also lower the carbon footprint and therefore is better for the environment. The over 450 technologies in our kitty as on today are mainly aimed at the micro, small and medium enterprises, and therefore this is very important for us. Today, as our distinguished speaker, we have Padma Bhushan Professor Padmanabhan Balaraman, who will be speaking to us. He obtained his BSc in 1967 from Pune University and MSc in 1969 from IIT Kanpur. He obtained his PhD in 1972 in chemistry from the Carnegie Mellon University, USA. He has worked as a research associate at Harvard University from 1972 to 1973 and later from 73 till 2014 as faculty of the Indian Institute of Science, Bengaluru. He was director of the institute from 2005 to 2014. Professor Balaram contributed extensively to the areas of molecular biophysics and chemical biology. He was editor of Current Science from 1995 to 2013, during which he authored over 300 editorials on diverse subjects related to science and scientists. Professor Balaram is recipient of many awards and honors, including the Bhatnagar Award, Padma Shri in 22 and Padma Bhushan in 2014, to name just a few. He is the recipient of the R. Bruce Merrifield Award 2021 of the American Peptide Society. Currently, he is associated with the National Center for Biological Sciences, Bengaluru, as the DST-YOS Chair Professor. Apart from doing science, I feel communication of science is of great importance to convince the world about our work and get recognition. Professor Balaram is an extremely effective communicator, and today he would be speaking to us about the contributions and the work of G.N. Ramachandran and the birth of molecular biophysics in India, reflections on a centenary. It is my great pleasure and honor and privilege to invite him to deliver the lecture today.
Thank you. Can I share my slides now?
Please.
Do you see it now?
Yes, sir. The slides are visible.
Okay. Thank you very much. Thank you very much, Dr. Singh, for that kind introduction and for the invitation to speak on Science Day. Now, Science Day really celebrates Raman's announcement of the discovery of the Raman effect, which he did for the first time publicly at a meeting of the South India Science Association at Central College in Bangalore. And at that time, Central College was still under Mysore University, so it's most appropriate that I remind you of this fact so many years later. This slide tells you what I want to talk about. I'm going to talk about one of Raman's students, probably his most illustrious students, and possibly one of the most illustrious of India's post-independence scientists, This year, when we are in the 75th anniversary of independence, we often reflect on what has happened over the last 75 years. We are sometimes told that nothing has happened for almost 60 or 70 of those 75 years. Now, in science, this is certainly not true. Many wonderful things have happened in the years since independence, and Ramachandran's work on molecular biophysics and protein structures is one of them. So I'm going to tell you about Ramachandran's work. Raman would have been happy to have his student, actually his work talked about, and you will see why this is so from the next slide. On the next slide, I show you two documentary pieces of evidence. I don't believe this have been seen by anybody before this. The first is Raman's recommendation to Madras University on the 19th of February 1952, recommending G.N. Ramachandran for a professorship at Madras University. At that time, Ramachandran was not yet 30 years old. He was only 29 when this letter was written. And what Raman says, of course, that I feel sure that Madras University could make no better choice for its professorship than Dr. G.N. Ramachandran. This is in 1952, February of 1952. G.N. Ramachandran was born in October of 1922. So we are really now in the Ramachandran Centenary year. And I thought it most appropriate that I show you this letter, which tells you the kind of feeling that Raman had for his student Ramachandran, who was extraordinarily independent, remarkably accomplished mathematically and in physics. But barely 11 years after he had written this letter, Raman nominated G.N. Ramachandran for the 1963-1964 Nobel Prize. I show you here the Nobel nomination, which is from the Nobel archives, which are now open until 1968. I do not know whether Ramachandran had any other nominations after this period, but certainly this one is on the record, and it was by none other than C.V. Raman. This morning I saw an article by one of India's prominent science journalists writing endlessly once again about how India has not won a Nobel Prize since C.V. Raman, and how and what we should do to get more Nobel Prizes. The answer does not lie in trying to get a Nobel Prize. On Science Day, we should remember that the answer lies in trying to do good science, and that is what, and fundamental science. That is what Ramachandran really did. Ramachandran was Raman's student in the Department of Physics at the Indian Institute of Science. And I had the privilege of being the director of the Indian Institute of Science when it celebrated its centenary. That year, we brought out a postage stamp with the help of the Department of Posts. They told me at that time that we could not have a picture of a single individual on a stamp. So I asked them, can we have a picture of many individuals on a stamp? They said they had no objection. So here are the many individuals who have been associated with the history of the Indian Institute of Science. I had the man who founded it, the Maharaja of Mysore who gave the land and promoted it, the secretary to Jamshed Tata who really pioneered all the work that was to be done with the British government, the first British director, Satish Dhawan, C.V. Raman, of course, who was the most illustrious director of the Indian Institute of Science. And then we needed to put someone who'd been a student at the Indian Institute of Science. And then, of course, we put G.N. Ramachandran. He was also the man who received the first Distinguished Alumnus Award from the Indian Institute of Science when it was instituted. And you see just Ramachandran is pictured on the extreme left of your screen. And you can see three wavy lines going up above his head. That is a representation of the triple helical structure of collagen, which I'm going to tell you about. But what Ramachandran today is most famous for is what is called the Ramachandran plot. And understanding the Ramachandran plot is really understanding the story of what I might call the stereochemistry of polypeptide chain configurations. This is the title of his first paper in the Journal of Molecular Biology in 1963. The origins of this paper are what I'm going to describe. You will see many of you are trained in chemistry and biochemistry. You will note that he's used the term configuration. And later on, we use the term conformation. This is because in the area of polymer chemistry and organic chemistry, the terms configuration and conformation have sometimes been used interchangeably. Ramachandran's work focused on the structure of proteins, and I don't need to tell an audience at CFTRI why proteins are important. We, of course, recognize proteins as important in nutrition, but proteins are important everywhere. There's no better way of illustrating the importance of proteins than to show you these pictures of the coronavirus. The coronavirus is a public health nightmare, an artist's delight. And the best definition of a virus that I've seen is one by Peter Medawar in his book From Aristotle to Zoos. If you go under V and look for virus, you will find a virus defined as a piece of bad news, which is the nucleic acid wrapped up in protein. And the protein that we really worry about so much is the protein on the surface of the virus, the so-called coronavirus spike protein. I will show you the spike protein. Today, we can understand the spike protein in complete atomic detail. We can see how the polypeptide chain folds in three-dimensional space. Computer graphics allows us to make colorful and aesthetic pictures of the protein. And this is what the spike protein looks like. The trimer on the right, the monomer on the left. But that's not the subject of today's conversation. What I want to really tell you is some history. And the history, this will be the historical background to Ramachandran's work of the 1950s and 1960s at Madras University. What did we know about proteins in the mid-1930s? Today, it's very important to think about the mid-1930s because the mid-1930s were a time of great historical political ferment in Europe and all over the world, leading up to the events which led to the Second World War. Today, we face similar kinds of ferment once again in Europe. In the 1930s, Linus Pauling, arguably the greatest chemist of the 20th century, had begun to turn his attention to the structure of proteins. He was also interested in the immune response. He was interested in antibodies. And so he began to collaborate and learn about immunology with one of the founding fathers of immunology, Karl Landsteiner, at the Rockefeller University, who won a Nobel Prize for his demonstration of the blood groups. Landsteiner wrote a famous book called The Specificity of Serological Reactions. It's a classic. Anyone who's interested in immunology should read it. Pauling had a copy, a personal copy given by Landsteiner, and on the sides, based on the evidence which was then available about antigen recognition by antibodies, he said, I think the protein must contain side chains with active groups. This was 1936, and I show you Pauling's notes on the book, which he had, his personal copy, picked up from the Pauling blog. Now, it turns out, of course, that proteins today are well understood thanks to X-ray diffraction. And an all-atom structure of a protein, which consists of tens of thousands of atoms, looks like that impossible collection of dots on the top left corner of the slide. But if you look just at the polypeptide backbone itself, without worrying about the side chains which Pauling talked about, then of course you get these more pleasing pictures of the polypeptide backbone, which folds around in three-dimensional space. But our first understanding of protein structures began to come in the early 1950s from Pauling's work and from the early X-ray diffraction studies which were beginning to appear in England. This book, which appeared in 1969, is called The Structure and Action of Proteins by Richard Dickerson and Irving Geis. This is a book which I saw for the first time when I came to Bangalore as a young lecturer to join G. N. Ramachandran's Molecular Biophysics unit at the Indian Institute of Science. And here you can see those shaded blue planes are the peptide planes. And you can see the peptide planes now connected to the next plane by a tetrahedral carbon atom. So the entire problem of polypeptide chain folding really was how these planes were oriented to one another about that linking tetrahedral carbon atom, which is a C alpha carbon atom of the amino acid. I will show you how Ramachandran approached this problem. Pauling approached it differently. Pauling approached it by looking at planes as drawn in this picture and produced the structures of the 310 and alpha helices. He did this very early on in 1951. And today, if you look at a textbook, you will find these are the kinds of pictures that you see of the two secondary structures that you see in proteins. The polypeptide chain winding around, and then you find hydrogen bonds between the backbone amide groups, the beta sheet with hydrogen bonds which run perpendicular to the long axis, the alpha helix with hydrogen bonds, those dotted lines lying parallel to the long axis of the structure. But as we go along, we come to the Ramachandran map. What does the Ramachandran map really tell us? The Ramachandran map has two parameters along the x and y axis, the dihedral angles phi and psi. And to tell you what a dihedral angle is, you'll have to look at my face now or my figure as I show you this on the screen. I now have four atoms which are connected to one another. The four atoms are the tips of the pens that I have. And then what will happen is that if all of them lie in one plane, the dihedral angle will be 0. Now, if I start rotating them one out of the plane, you will find that I now have three-dimensionality entering this. This is for a connection of four linked atoms. So when we have just two linked atoms, we just have the pen, and we have a distance between the two ends of it, the two atoms, a bond length. If I now have three atoms, then of course I will get, and I don't know whether you can see it. If you can see my face, you can see this. You will get two bond lengths and an angle. But if I now have four atoms, you will get the dihedral angle, which I show you on this slide. Ramachandran recognized that the connection of two peptide planes connected to a tetrahedral carbon atom where I point my cursor, that connecting hinge now really determines the orientations of the peptide planes. This meant that the 2 degrees of freedom for every amino acid were the two dihedral angles, which he termed as phi and psi. Now, if you have a collection of amino acids, you might have 100 of them, then you have about 99 pairs of phi psi values. So this would then mean that you have an enormous three-dimensional problem. But the Ramachandran map reduces this problem in 3 dimensions to an analytical problem in 2 dimensions, where both the axes, phi and psi, are basically 3-dimensional parameters. So if I may be allowed to simplify, this is transformation of a 3-dimensional problem into a 2-dimensional analytical problem. Now you might ask, in this enormous phi psi space, conformational space, what are the allowed conformations of polypeptides? Those allowed conformations are determined by the contours of the Ramachandran map. And you can see that only about 1/3 of space is actually allowed. This is an enormous simplification of the protein folding problem, a problem which had not been identified at the time that Ramachandran really drew this map. I'll show you 2 assessments of Ramachandran's work, recent ones, 21st century. This is one in a paper in the Proceedings of the National Academy by George Rose. And he says, no general biochemistry textbook is complete without a phi psi map of the alanine dipeptide. This iconic plot is a compact representation of a profound organizing idea, one that ranks among the fundamentals of structural biochemistry. On Science Day, it should make you feel proud that an a work from India done in the 1960s, when we were not as advanced as we are today, finds its place actually among the immortal works of biochemistry. Here is another one from about a decade ago. And then it says that the Ramachandran plot is an iconic image of modern biochemistry. And then it says, after all the analysis that has been done in the 50 years that have followed, it says, we find no need to invoke additional interactions to explain the backbone conformations of proteins. At CFTRI, where you're so much concerned with proteins, you must now look back once in a while and pay a tribute to Ramachandran, who did more than any other Indian to give us our present understanding of protein structures. But I'm going to start with Ramachandran's early work. Ramachandran's early work was on the alpha helix, was on the collagen triple helix, my apologies, was on the collagen triple helix. And what I have is a picture of him looking at Pauling's alpha helix and his own triple helical structure. The Ramachandran map I show you again before I go away to collagen. You can see it now in color, the way it appears, and I will show you this again later on, so we won't worry too much about it at this point. But many years ago, my interest in this area was sparked by this article which appeared by David Eisenberg in the Proceedings of the National Academy of Science of the United States in 2003. This was a celebration of Pauling's discovery of the alpha helix, beta sheet, the principal structural features of proteins. And in this article, I saw this paragraph. And what Eisenberg had written was that today, the Ramachandran diagram is taught in all classes on protein structure and is featured in every textbook to give insight into the forces that determine the structures of proteins. Then he went on to add what I thought was a rather provocative paragraph. He said, but there is nothing in this diagram beyond what Pauling and Corey knew well. They built models of their proposed structures that embodied all features of the Ramachandran diagram. Apparently, they understood the principles so well that they felt no need to explain them by a diagram of the sort. This, I felt, was almost an insult to the memory of Ramachandran, who had passed away in 2001. It was at that time that I really began to look at the history of protein structures, and that is what I'm going to show you now. In 1943, Maurice Huggins wrote a review in Chemical Reviews. It has the hydrogen bonded structures. Maurice Huggins, for those of you who have not heard his name, is the man who really introduced the hydrogen bond into the literature of chemistry. He did this as an undergraduate student at Berkeley in turning in an assignment for an undergraduate course. This should be a lesson to all those people who believe that there is nothing to be gained from teaching in undergraduate classes. Sometimes you might stimulate a student to do things that one cannot do oneself. A few years later, in 1950, this paper appeared, Bragg, Kendrew, and Perutz. When I give you these dates, look at these dates carefully and remember them. It's important to remember your history. Why are we in the position that we are today in India? It is largely because our inability to understand history in terms of documented history and to only worry about things which are undocumented. In science, everything is documented. This paper appeared in 1950 in the Proceedings of the Royal Society, and the most distinguishing attribute of this paper is that every structure in this paper is wrong. And not only is every structure in this paper is wrong, this is the only paper that I know of in the literature in which all three authors won the Nobel Prize. Lawrence Bragg had already won the Nobel Prize for his introduction of X-ray diffraction to the study of crystals. John Kendrew and Max Perutz would win the Nobel Prize a dozen or years later for their work on the structures of myoglobin and for determining the X-ray structures of myoglobin and hemoglobin. But this was the prelude to Pauling's work. In 1951, Pauling, by model building, got the structure of the alpha helix, and all of you know about the alpha helix. This is Pauling in Madras in 1967, showing a picture, showing a model of the alpha helix. And he came here to visit Ramachandran in his department. 1951 was the alpha helix, 1950, 1951. 1953 was the DNA double helix. Ramachandran went to Madras in 1952 as professor of physics, and he was looking for a problem to do. This is something that everybody who's looking for a research problem must do. When you look for a research problem, you look for problems that you're familiar with. You look for problems that you have done before. Ramachandran looked around for a problem. J.D. Bernal, who was visiting, suggested that maybe the structure of collagen would be something that could be done by X-ray diffraction, and he was unhappy with the structures then proposed for collagen. The Central Leather Research Institute in Madras was next door to the department where Ramachandran began. And it turned out that it was easy to obtain rat tail tendon from there, and so the experiments began on trying to get fiber diffraction photographs of collagen. The fiber diffraction photographs of collagen looked like the picture that I show you there. Spots, very few, and smears. And it is from this kind of diffraction data that the people who were then building the structures of nucleic acids and proteins tried to build the polymeric structures. The collagen triple helix emerged from limited diffraction data and from enlightened model building. On this slide are pictured the two principal architects of the collagen structure, G.N. Ramachandran and his colleague, his postdoctoral fellow, Gopinath Karta. Both of them are no longer with us, but when you look at the triple helical structure of collagen, you can see that it is more complex than the alpha helix. It's more complex than the double helix. And then I will show you on the next slide its importance. It's in fact the most abundant mammalian protein. It's the major component of bone, tendon, cartilage, and teeth. Today, if you look at the Central Leather Research Institute, collagen dominates their discourse. It has an unusual amino acid composition, and I will show you that amino acid composition on the next slide. Since proteins are polymers of amino acids, collagen has this remarkable composition: glycine, proline, hydroxyproline, a tripeptide repeated over a long length of the polypeptide. When you see a sequence like this, you must make an inference. Ramachandran and Karta immediately made that inference. There's a certain repetition here. Amino acids which cannot form backbone hydrogen bonds, proline and hydroxyproline. Glycine, which is the smallest amino acids. And today, most of you, if you are students, if you look at the 20 coded amino acids, how do you categorize them? Glycine and proline you set apart, and the other 18 together, because glycine is the smallest, proline is the only one which cannot form hydrogen bonds. The result of this is that if 1/3 of the amino acids are glycine, you would imagine that the structure must be a threefold structure. Ramachandran then and Karta began to work on what you might call threefold structures or triple helical structures. And these are the kinds of structures that they came up with. In later years, I've heard Ramachandran describe the triple helix in his own words. He says that he got this idea when he saw his wife plaiting her hair. And then you can see the coils going one around the other. This now becomes a structure in which three polypeptide chains sort of coil around one another, eventually to give you the triple helix. With glycine being the smallest amino acid, it must come in the center, because if you put anything else there, there will be no more space. Today we know that diseases of collagen happen when you have a mutation from glycine to alanine. So this is the background to the collagen structure. But historically, when you look at it, look at the dates. The first paper, 1954, in Nature. Second, 1955. Third, 1956. When did the DNA double helix paper appear? It appeared in 1953. Now you can see why C.V. Raman actually nominated G.N. Ramachandran for the Nobel Prize. Raman nominated Ramachandran for the Nobel Prize largely on his work on the collagen structure, which was at the time that it came out possibly the most complex structure of a fibrous protein molecule. Companion papers which appeared in 1955 by Francis Crick, Triumphant After DNA, and Alex Rich, 1955, two papers critical of the Ramachandran structure of collagen. And what was the criticism? The criticism really was that the structure was unsatisfactory because there were bad steric contacts, that is, atoms came too close to one another. And this criticism is what led to Ramachandran's even greater work on the Ramachandran plot. This is a letter written by Ramachandran in August of 1954 and the response from Linus Pauling. And what Pauling says is that he thinks that the structure is largely correct, but unsatisfactory in some respects, in particular the bending of hydrogen bonds. You can see Pauling is already thinking about detail. The gross elements of the structure were in fact correct. This is what the physics department looked like at Madras in 1955. You see Ramachandran, the man with the tie, sitting there in the front row. Next to him is Gopinath Karta, characteristically wearing a dhoti. He came from Kerala, always wore this when he could. And then you see some people who were in later years famous in the department which Ramachandran founded. V. Shashishekaran on the top, R. Srinivasan also circled. But I show you some letters here. These letters are written by Alex Rich and Francis Crick. And he says, we should be very glad to have your comments on these remarks. That is, we are holding a seminar on collagen on 14th December, and we would like to present your latest ideas on the problem. Maybe do this. Or perhaps you would prefer Dr. Karta to do it, because Dr. Karta at this time was already in England. On the next slide, these are letters written by Karta to Ramachandran in December 4th of 1955. They are handwritten, they're hard to read, they need to be transcribed, but I've tried to do my best. He says here, Dr. FHCC, that's Francis Crick in Cambridge, was telling me, I do not know what he meant, but the general idea seems to be that the publication of our paper was purposely delayed by months for them. And the them was Randall at King's College in London to work up our idea of after seeing the manuscript. So it turns out that there were competing groups. This is rather like the DNA structure. The groups are the same. Crick in Cambridge, Randall at King's College in London. Most of you will remember the double helix story. Unfortunate part is most people don't like to read. You should go back and read. And if you read it, then you will find that this story is very similar. There's another letter from Karta a day later in which he says, I'm also worried about the large number of free NH groups, and that from that point I would prefer a 2 hydrogen bonded system, even though that involves bad contacts and a bit of strain to make R2 a proline. When I read this, I thought the amount that Ramachandran and Karta knew about the structure of proteins was very much more than what most of us knew in the 1970s. Ramachandran on collagen many years later said how it was. 51 Pauling and 53 DNA, and he says the helix era had begun, and he contributed to this actively with the triple helix of collagen. He goes on to add many things here, but I won't read this to you, but just summarize this by saying that here are the 3 helices of biology. Pauling 51, the alpha helix, Watson and Crick 53, the DNA double helix, and Ramachandran and Karta 1954, the collagen triple helix. This, at least on Science Day, should make you feel a little bit proud about what post-independent science has done. Many years later, Linus Pauling said this. He said that in 1951, he and Robert Corey had proposed a structure for collagen involving 3 polypeptide chains twisted about one another. It is well known that our structure turned out not to be right. And then he says, at that time, he'd suggested that they should be allowed 2 guesses on collagen. But then he says that Ramachandran and Karta described the striking triple helical structure of collagen that is now generally accepted as being essentially correct. This is from the presidential address that he gave at the 1967 symposium in Madras, where he showed the model of the alpha helix. Many years later, Francis Crick wrote a book, What Mad Pursuit, on a scientific autobiography. And he had a section on DNA and collagen. He says, and I won't read all of it to you, but just to say that the basic fiber of collagen is made of 3 long chains. All the elements that surrounded the discovery of the double helix surrounded that of collagen. The facts were just as confusing, the false solutions just as misleading. Competition and friendliness also played a part in this story, yet nobody has written even one book about the race for the triple helix. This is surely because in a very real sense, collagen is not as important a molecule as DNA. But then he goes on to say, this of course depends what you consider important. He says, after Alex Rich and I worked on collagen, we tended to be rather patronizing about it. After all, we said there's no collagen in plants. In 1955, after we got interested in the molecule, we found ourselves saying, do you realize that 1/3 of all the protein in your body is collagen? So he ends, and this I think is the most important sentence. So as I have said before, it is the molecule that has the glamour, not the scientists. And my only conclusion would be a group in Cambridge would have been far more glamorous than a group in Madras University in the 1950s. Very much later in 2012, when single crystals of synthetic polypeptides corresponding to the collagen sequence were produced, crystallized, and diffraction structures obtained, the Ramachandran Ambadi structure was diffraction data was completely explained. And the conclusion was this, that the average molecular structure of collagen does not correspond to the prevailing Rich-Crick model, but corresponds instead to a triple-stranded 7-2 helical model. Technically, this is more or less the Ramachandran-Karta model. What was the criticism of the Ramachandran collagen structure? It was really that atoms come too close to one another. But then you might ask, how close can atoms come to one another? One can say they cannot come closer than the sum of their van der Waals radii. The van der Waals radius is a concept from physics. What are the real van der Waals radii of atoms and molecules? This is not really known. And in order to do this, Ramachandran and his collaborators, Shashi Sekharan and Ramakrishnan, all of them embarked on trying to get what were in fact experimental non-bonded radii for atoms from the available X-ray diffraction data on organic crystal structures. In 1961-62, when they were doing this, there were very few organic crystal structures. Also remember, there were no databases, there were no computers. 3-dimensional coordinates as X, Y, Z for every atom were actually printed lists of coordinates. And therefore, it required painstaking work in order to measure the distances between atoms. That is what led to the Ramachandran plot, which I'm going to describe. But what I'm going to show you now is, when did the Ramachandran plot acquire its name? It acquired its name when this book appeared, The Structure and Action of Proteins, which I showed you, in 1969. In 1969, Dickerson, in his book, put this picture and called it the Ramachandran 5-psi plot with contours we won't worry about those contours because that is now a technical issue. He also went on to say that the Ramachandran plot is central to our understanding of the way polypeptide chains fold. But the early origins of the Ramachandran plot can be seen in plots like this, which appeared in the proceedings of a symposium at CLRI in 1962. This is Shashishekaran now, another plot now in the period 1960-1962. And this is the famous paper which I showed you. The plot looks different simply because the conventions have now been changed from dihedral angles ranging from 0 to 360 to minus 180 to plus 300 to plus 180. This is how the plot looked in the Ramachandran paper. And much of the computations for this plot were done by my former colleague, my late colleague, Professor Ramakrishnan. This is what he looked like in 1967. This is the kind of calculator he used, which had only these elementary arithmetic operations. So it was a major task. Many years later, he taught the ideas of the Ramachandran plot, calculations of dihedral angles, construction of the plot, and this is Ramakrishnan teaching that to students at the Indian Institute of Science, Education and Research in Pune in 2009. But really, if you look very carefully at the legends in the Ramachandran paper, you will find that the legends are interchanged. What we call today the Ramachandran plot has the wrong legend in the original paper. Two legends have been interchanged by the printers. Although this was known to everybody, nobody ever said anything about it. Many years later, I was editor of Current Science and I produced a special issue on the Ramachandran plot and put it on the cover. At that time, I asked my colleague, Professor Ramakrishnan, can I now put a correction to the legends? He said, no, don't do this. Professor will be angry. You're going to present him with a copy of this special issue. So I let the plot remain, but today I will show you the correction. All this appeared at a time when very little was known about the structure of proteins. This is a paper in Nature in 1965 by David Phillips describing the first structure of an enzyme, lysozyme. And now you can see David Phillips demonstrating at the Royal Institution in 1965 what a globular protein structure would look like. And if you didn't do it and stretched it out, this would of course correspond to the Ramachandran angles of 180 and 180. Then it would reach all the way to the roof of the Royal Institution and beyond. This is how the Ramachandran plot appeared in a famous review article in Advances in Protein Chemistry in 1968. If you haven't seen this article, you should. It's more than 50 years since this article was published. It still draws enough citations to make most of us envious. In the late 1980s, in 1988, I was at the University of California in San Francisco. And I was in the Department of Biophysics and Crystallography, which had a small library. And I went into the library and picked up the Advances in Protein Chemistry and was thumbing through the volumes. And then I found that the one chapter which had the most marks on it, graduate students having written all over it, was the Ramachandran Shashishekaran article in Advances in Protein Chemistry. But you can see that Ramachandran was a difficult man because we were afraid to correct the error in the legends in 1963. In 1968, the editors of the Advances in Protein Chemistry said, by the author's request, the publishers have left certain matter of usage and spelling in the form in which they wrote them. They wrote well, they wrote correctly, but many times they may not have written in the manner in which American editors liked them. The Ramachandran map has evolved over the years. We now have it in various colors, but I will not go very much to this. But I want to address only one issue. Was Eisenberg's comment on the Ramachandran map correct? In 2001, the year that Ramachandran died, this article appeared in Angewandte Chemie. Pauling's left-handed alpha helix by one of his most famous associates, Jack Dunnett, a crystallographer who died a short while ago, remarkable crystallographer. And he asked a question, was Pauling aware of the absolute configuration result of barefoot? Did he really worry about absolute configuration of the amino acids? The answer is no, because all Pauling structures, which he wrote in his 1950-51 papers, were of polyglycine. Now, of course, what this would mean is that if you had a left-handed helix, it would lead to a bad contact, and you would then come to the conclusion that only right-handed structures would be possible for levo amino acids or the L amino acids, which are found in proteins. That, of course, becomes obvious when you look at the Ramachandran map, which I've put on the slide. I have overlaid the maps for the L-alanine and D-alanine residues, and you can see the angles that you determine from protein crystallography are only in conformity with the right-handed helix for L-amino acid structures. So Ramachandran really, Pauling and Corey had not anticipated anything that Ramachandran produced. Today, the Ramachandran plot is very useful. In 1990, for example, in this article, the article called Errors in Three Dimensions, it shows how crystallographically incorrect models can be corrected using the Ramachandran map. Ironically, one of the crystallographically incorrect models is due to David Eisenberg, which is the Rubisco model. Once again, Brian Matthews, another famous crystallographer, showing in his own work how incorrect models for lysozyme were then corrected using the Ramachandran map. So today, this is what the Ramachandran map looks like. That collection of black dots that you see on the left are experimental points determined from protein structures. That's an experimental Ramachandran map. It corresponds perfectly to the theoretical Ramachandran map using standard van der Waals criteria, which Ramachandran used many years ago. Today, of course, you can make it look attractive in 3 dimensions with the intensity of points along the 3rd dimension. And you can see that the alpha helix points are somewhat more clustered than the extended region where both the beta sheet and the collagen structures actually appear. But these are matters of detail. Today, all of you are in fact prisoners of Scientometrics. I have not come across any student in India now, PhD student, who does not worry about the impact factor of the journal in which they're going to submit their paper. What one should worry about is not the impact factor of the journal, but really the impact factor of the work that you're publishing. We can ask now, how do citation statistics, what do they tell you about Ramachandran's work? A lot of analysis can be done, but I show you just one slide. This is Ramachandran's 1963 paper in the Journal of Molecular Biology. And what one can use are Garfield historiographs, which are pioneered by the founding father of Scientometrics, Eugene Garfield. What Garfield really introduced Scientometrics for, citation indices and the Web of Science, was to trace the connections between scientific papers, to build a sociology of science, where you look at how ideas are linked to one another. How can ideas be linked to one another? They can be linked only when you look at what papers are cited in a paper. You can draw networks, connections, and from this you can learn a great deal. Now, Ramachandran's 1963 paper, you can see, beginning with 1963 in the top left corner, there are not too many citations. But as you keep going, the citations keep increasing like anything. This is what is called long-term impact. This long-term impact would not have been imagined by Ramachandran. I must put an arrow here where I show my cursor. That's the year that Ramachandran passed away. Ramachandran actually left the department in which I worked somewhere where the cursor is, between 1979 and 1980. So at no point in his lifetime was Ramachandran truly aware of the full impact of the work that he had done. His paper is cited, but there are papers which cite his paper even more cited. I show you just 3 of them. They lead to the peaks in this citation analysis. Those peaks are really the Chow-Fussman paper on secondary structure prediction, which most of you will use blindly. The Brooks paper, which introduced molecular dynamics, which again most people use blindly. And the validation of protein structures, which is now already encoded into the protein data bank, which uses the Ramachandran plot as the criterion to decide the validity of structures to be deposited. These are papers which have been cited tens of thousands of times. The molecular dynamics paper 13,000 times. The validation of protein structure papers 19,000 times. And when you look at these, the Ramachandran paper itself has been cited over a couple of thousand times. But you can see that from 1963, it is delayed impact. But each time there is a technological advance, science progresses. Remember that Freeman Dyson many, many years ago commented that science often advances more by new technology than by new concepts. The Ramachandran map was a concept, but the technologies which drove the application of the Ramachandran map are the technologies of X-ray diffraction, synchrotron radiation, high-speed computation, and the ideas of molecular dynamics. Did Ramachandran get his due in India? This is a question that we can ask on National Science Day. I believe he did not, although we now belatedly recognize him. And not too long ago, I was invited to speak at a function organized by the Government of India, where they celebrated the centenaries of many people, and Ramachandran was also allotted 15 minutes along with other centenaries. Now it turns out that when I searched the internet to see other references to Ramachandran and the Government of India, all that I found was this: the Income Tax Department having levied a penalty on him, which he protested, of course, because at the time that he retired, he went to America and earned a little money as a Fogarty Fellow at the National Institutes of Health. And it turns out that he eventually won his case on the 29th of April, 1982, where they decided that the money that he got was not a salary, but in the nature of scholarship. I want you to go back to the dictionary and look at the word scholarship. Scholarship has 2 meanings. It's something that is given to a scholar, and Ramachandran was a scholar. Here is a picture of the 1967 symposium. It's taken out from a larger group photograph. It shows you Ramachandran on the extreme right, Dorothy Hodgkin on the extreme left, Linus Pauling, and the then Vice Chancellor of Madras University, Lakshman Swami Mudaliar, who actually appointed Ramachandran as a full professor a few months short of 30 years of age, and encouraged him throughout his tenure as Vice Chancellor. Now, when you look at the enormous decay of Indian universities, you can see that that enormous decay of Indian universities can be largely attributed to the enormous decay in the quality of leadership that we've had over the last 30, 40, 50 years. Pauling came to Madras in 1967, and I couldn't find anything that he wrote, but I found a letter that his wife wrote to her son in 1967. And this is about her trip to Madras. She said, "We've been having a busy time. It's interesting too. I really can't see any future for India unless they change drastically. It is sad. The women do a lot here." And I thought I would show this to you because this was the impression that she got by going around India at that time. She found women overworked, and this is something that one is acutely conscious of today. But I think Pauling's wife, Ava Pauling, was probably wrong. There was a great future for India, which most of us have witnessed. But I think there should be an even brighter future if we take science truly seriously. Today, if you go back to the problem of protein structures, it's a much more detailed understanding of protein structures, which is likely to even make us understand in retrospect what the virus has done to us over the past 2 years. You cannot believe everything that you read today, but you might be able to get a much more academic and a much better understanding maybe a few years hence. Finally, if you want to know more about G.N. Ramachandran and people's impressions of him, I would urge you to look at this documentary produced by students of the CSIR in Pune entitled The Trials and Triumphs of G.N. Ramachandran. It is available on YouTube and all of you should be able to see this. Lastly, I would just like to make a comment. The comment is, science should not be something that is celebrated by government and government institutions as a token recognition of the importance of science on the 28th of February every year. Tokenism does not lead science very far. One of the things that needs to be done on Science Day is to understand the things that were done in the period between the 1950s and 1960s, when many scientists who had grown up in the fervor of the independence movement and who wanted to dedicate their lives to the service of India worked very hard to do wonderful things. Institutions like your own are not what they were when they began. All Indian institutions tend to decay. Some stagnate. The ones which stagnate are the ones which we celebrate. They do not march on a course of progress continuously from decade to decade. It is this fact that we must acknowledge on Science Day, and it is this fact that government too must acknowledge on Science Day. Lastly, I would only like to acknowledge the two institutions which have provided me shelter throughout much of my professional life. In fact, I should say through all my professional life. The Indian Institute of Science on the top left, all the way till my retirement, and the National Center for Biological Sciences, the bottom right, which has provided me a post-retirement home. Thank you very much.
Thank you so much, sir. It was really very, very interesting to hear about the history of how the structure of collagen was discovered, as well as the triple helix model and the Ramachandran plot. Indeed, I had goosebumps all the way when you were speaking about, I think it was like a Bollywood movie. The romance was there, knowledge was there, competition was there, politics was there, emotions were there, all of it put together. Probably if it were in the West, it would have resulted in the Nobel Prize. Definitely, I do believe that. And but nevertheless, Professor Ramachandran's contribution was really tremendous, and your storytelling would make all the youngsters present today to realize what a great contribution it is, and we pay our tribute to him. Definitely, we are also working on proteins in CFTRI, and you have brought home to us how important fundamental knowledge is it, so that we can find applications. We do look at proteins from nutrition point of view, be it the digestibility, bioavailability, and stability. And definitely the fundamental knowledge helps us to apply either enzymes or proteins to get foods that will be more digestible, be it for geriatrics, infants, or even to make certain foods that are specifically required for targeted population, either sports or metabolic disorders and so on. Indeed, I speak for all my colleagues and whoever has joined here today to once again thank you very much for this very, very interesting lecture. And I do agree with you that we need to look every day as Science Day, and to also understand where we are going and how much we stick to our mandate. And definitely, we do need to keep rediscovering and aligning ourselves to the national needs. Once again, I thank you very much, and I hand it over to Purnima now.
Thank you, ma'am. As you rightly put, it was a captivating talk. Thank you, sir. Thank you, Professor Balaram. Thank you for explaining us the complexity of protein structure, conformation, and Ramachandran plot in a simple way with the historical letters and pictures. It was indeed a great talk. Thank you for taking us through the Ramachandran's life, his relationship with his mentor, Sir C.V. Raman, and his students, Karta, an example for all the student-teacher relationships. Thank you for remembering the long association of Odears, Mysore in the history of science, Indian science. Thank you so much once again, sir, for accepting our invitation and delivering this wonderful lecture on National Science Day. I thank you, ma'am, for her thing, and I thank the whole CFTRI family for their support and encouragement in conducting this particular event. Thank you, one and all. Thank you, sir.
Thank you.
Thank you, sir.